Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on aside as we review Chapter 3 in the Big Ideas Math Integrated Math 2 textbook, where we graph quadratic functions. We start from very basic ones with very little transformation except for flipping and stretching, and then we do some translations along the way. We look at all the different forms, and I think in the very last section we're comparing exponentials to quadratics to linear functions and all that. I'm sure we're going to write equations, but a lot of things regarding graphing. So strap in for that. If you'd like to download this Chapter 3 review of, I think, 35 questions, something like that, download it in the description section down below in the PDF. You can also download graph paper that I'm going to be using if you'd like to, and print all that out or use it however you'd like to, or just watch this thing. And if you want to find a specific problem, down in the description section, you can find each problem by number. So you can find those ones, and if you want to find more of this stuff, as far as sections 3.1 to 3.7 in my IM2 playlist, you can find that. And following this video is the Chapter 3 test and cumulative assessment in the Big Ideas Math Integrated Math 2 textbook. Without further ado, guys, that's a lot of words. Let's go ahead and get started. We're going to begin with section 3.1, graphing f of x equals ax squared. The parent function of x squared is just having a vertical stretch factor applied, which can also flip the graph over. So the very first example they have is graphing some g of x equals negative 4x squared and comparing it to the parent function f of x equals basically 1x squared. That 1x squared graph is right here in black. Normally you'd see it stretched a lot taller, but it looks like they compressed the y values by going up by 4s, so they could fit more points on this bottom one that's negative 4x squared. Now they use a table. I'm less inclined to do that myself unless I'm required to. If you see me use vertical stretch factors before and apply them, I'm going to multiply my general 1, 4, 9, 16, those values by whatever a is. Case in point, 0 squared is 0 times negative 4 is 0. 1 squared is 1 times negative 4 is negative 4. 2 squared is 4 times negative 4 is negative 16. So that 1, that 4, that 9, 3 squared, is multiplying by that. So I'll do some more of that instead. Anyway, they plot the ordered pairs in blue. Remember the scaling. X's is going by 1. Y's are going by 4. And then they draw a smooth curve with arrows indicating the all real number domain and the less than or equal to 0 range. Now, they write a comparison of these two. They state what's the same with them. I feel like I'm not going to state what's the same. Every time f of x is x squared, the vertex will be at the origin, axis of symmetry on the y-axis at x equals 0. But we'll talk about what's different. And in this case, there's a vertical stretch factor of 4, and it's reflected over the x-axis, which is what they're describing here. So let's go ahead and try 4 of these where we're going to graph the function and compare it to the original. I think the way I want to start these off, here is I'll copy and paste one of these graphs. So if you want to find the scaled ones, you can. And I'm going to draw the parent function now. And then I'll just go ahead and copy and paste that over to each problem that we do, if that's cool. Because there are going to be 4 of them, I might as well just use it each time instead of redrawing it so we can compare. Assuming I'm going to use the same graph thing each time, and I guess I will. Oh, I need to draw the curve still. Give me 1 second. So this is the parent function, f of x equals 1x squared. It's got that 1 squared is 1, so 1, 1. 2 squared is 4, 2, 4, and 3 squared is 9, 3, 9. And on the other side of this, across the axis of symmetry, right here, are points of the same height, the same distance away. Negative 1 squared is 1, negative 2 squared is 4, negative 3 squared is 9. This is our f of x equation. However, for this problem in number 1, and I'll go ahead and copy that to get ready to paste later. On number 1, we're going to be graphing g of x, or p of x, equals 7x squared. Now, this will be a very tall graph. There's not a lot that we can kind of really say with this, but the vertex is at the origin. No change there. The only change is a vertical stretch. Instead of 1, 1, we'll go 1, 7. 7 times 1, boom. Very tall. The description on the example question, I don't know if you saw it, but the description talks about this graph being narrower. It's not wrong calling it narrower, but to think that it doesn't hit the same x's as the other would be false. Both of these graphs feature an all real number domain. There's no restriction on x. I'd rather instead call it taller, but then again, there's no restriction on y's range either. It's just that the y values are higher up for the same x values. So that would be the p of x thing. And as we describe it, as I need to describe it, we'll go ahead and say, I'm just going to state what the a value is doing. And I know that that's not very much to say in detail, but there's a vertical stretch. P of x is vertically stretched by a factor of 7. And that's really all I want to describe whenever I talk about A, whether it's vertically stretched or compressed, and whether it's reflected, flipped over or not. That's really all I'm going to go for. And I'll talk about the rest out loud there. Number two, and as I paste this and bring it on over, second time we will do this for Q of x equals 1/2 x squared. I think here you're going to see more character on this graph. So number two, Q of x, we are going to vertically compress this graph. Instead of going 1, 1, take half of 1 and get a half. Instead of 2, 4, half of 4 is 2. Instead of 3, 9, half of 9 is 4.5. Now I can fit more points than the other graph could because I can do half of 16 and get 8. And if I use the taller version of this graph, I could fit quite a few more points. I'm sure you're going to see me do that on some taller graphs later. But because I already have this parent function set up with this, I'm just going to go ahead and keep it like this for now. So here's this graph for Q of x, vertex still at the origin, no change in translation for any of these problems in this section. So get used to that. This graph could be argued to be wider, but what we're really seeing instead is, remember we said instead of at 1, it's at 1/2, half the height. Instead of 4, it's at 2. So really what we should be doing is comparing these guys here, showing how it's shorter, and then even at this one here, it's shorter than whatever it would have been above. This is what we call a vertical compression. So Q of x is vertically compressed by a factor of 1/2. And we got to state vertically because you can also do horizontal compressions and such. I don't know if we're going to be talking about those in these kinds of problems, but kind of just be ready for anything in a review. Number three, we have G of x equals -3/4 x squared. Now, last time I pasted it went right in that area of the window, so let's do that and then bring it on over. Okay, so -3/4 x squared. We're going to take 3/4 of the heights, which isn't one that we commonly do, but I'll use the fractions best I'm able. We'll see how I do. But we got to flip it over. That's what the negative's going to do. So instead of going up, basically, I'm going down. How much am I going down? I'm going down 3/4 of 1. That's 3/4. I'm going down 3/4 of 2. 2 divided by 4 is 1/2, and half of that is 3 halves, I should say. So -1.5 there. So 3/4, no, is that right? Hold on. Not 3/4 of 2, I'm sorry, 3/4 of 4. 2, 4, hold on. 3/4 of 4 is -3. I was going to say that's linear. So -3. 3/4 of 9, I don't know. 27/4 is 6 3/4. So -6 3/4. Those ones are a little tougher to play with. I don't know. I've not really done 3/4 a lot. 3/4 of 16 is 12. Now that can't really fit on this very well. I'll just plot it down there. But you're getting the idea of it, the essence. So -3/4. I'm flipping this over this axis of symmetry right here, which, by the way, is still at x equals 0. And at least we're getting the essence of the graph as we sketch that curve. Now, how different is this from plotting in a table? Not much. I'd say plotting in a table is just more writing work and obviously sketching out a table, because I'm still calculating the same things, but I know I should be doing it 3/4 of 1, 4, 9, and 16. And look at me, I accidentally did 3/4 of 2 at one point. But 3/4 of 1, 4, 9, and 16, and 25, and all of those. So I think it's faster for me to work that out anyway. All right, so what are we doing? First thing we're doing that I want to state is the negative portion. We're reflecting over the x-axis. That's what that part of the A value is doing, the negative. And then we're vertically compressing, since it's less than 1, factor of 3/4. So this graph is wider than the black original f of x graph. By the way, I didn't label this one, or probably the previous one, but this is G of x right there. Okay, and lastly, number 4, from this set, we have h of x equals -6x squared. Again, this will be a very tall graph like that 7 one. Whoopsie, pasted way in the wrong spot. Sorry about that. So over here, we have number 4, h of x equals -6x squared. Also flipped over, but also very tall, or narrow, if you will. Instead of 1, 1, it's 1, 6. Right, now there are just no other points I can fit. If I want to do 2, 4, over 2, instead of up 4, we go down a certain amount. I got to do 4 times 6, which is 24. Even with my tall graph, I can't fit that, so I'm not going to bother. I won't try. But you multiply those things by 6. There's a vertical stretch there as we mosey on forward. So how do we say it? We got 2 sets. Reflect over the x-axis. 1. Reflect over x-axis. And also, and I should say h of x, but we know what it is. Vertically stretch by a factor of 6. Now, don't say negative 6. We already mentioned that with the reflection. There's h of x. There are the first 4 problems. Get used to a lot more graphs, and hopefully that's making sense without actual use of a table. Otherwise, we would be here all night. Number 5, identify characteristics of the quadratic function and its graph. Well, interesting. Oh, okay. I was going to say, if we have to come up with an equation, interestingly enough, we can't write one based on this ax squared because there would be more of it. But, you know, and I haven't done this stuff in a while to know exactly everything they want, but I think they're going to ask for the vertex, the axis of symmetry, the whether it opens up or down. I don't remember if that's a very specific thing that they ask for, but that makes sense. And actually with that, I forgot, they would ask about the maximum or min value. Max, min. And domain and range. I can't guarantee, was there end behavior? I'm going to state it if this isn't something that you guys do. I can't remember what all these things had. So I'm going to list all of them for this graph, and anything that you can pick up on that makes sense to you, go ahead and do it. I'm sure I overstated, and that's totally okay. But we're not going to write the equation. Not yet anyway. We'll save that for another section. All right, the vertex of this opening up, by the way, facing graph, is at 1, -3. Now, the axis of symmetry is this vertical line right here. That's the line x equals 1. So axis of symmetry is x equals 1. It's the same as the h value of your vertex there. By h, I'm referring to in vertex form of a graph, the x value of your vertex. The max or min, it has a min at -3. -3 is this value here. That's the lowest that the graph goes. There is no maximum. It goes up, but it goes up forever. So there's no maximum. There's no ceiling. The domain is all real numbers. This thing goes as far left and right as the eyes can see. It goes as far left as -1 and as far right as 3 in the window range, but it keeps going forever as it continues to go up. Speaking of going up, there is no limit to where it can go upwards, but there's a limit to where it can go downwards. Y values must be greater than or equal to -3, given that that's the min. I definitely overstated on these bits here, but that's okay. The end behavior, and this is the part that I don't know we're actually doing, so you can totally ignore this, even no idea what I'm talking about. As x approaches positive infinity, as we go right forever, you see the y values trend upward forever. And then as x approaches negative infinity, as we go forever left, the y values are still approaching upwards forever. So those are all the characteristics that I feel I can lay out. I probably overdid it, not remembering which things we were going to do and weren't going to do. So that's a nice set there. That closes off section 3.1. Now we go to section 3.2, where we get to do ax squared plus c. That means there can be vertical translations. Our axis of symmetry will still be on the x-axis here. That means no change in x on vertex this way, but we will be able to change up and down. Now, for myself, when I do the graphs, I'm going to be starting with the shifts first, the translations, and then I'm going to graph with respect to there. So I'm not going to use a table. I'm going to be using 1, 1, 2, 4, 3, 9 kinds of things from my vertex. And I'll do that here on out. Before we hit number 6 officially, let's take a look at the example that they do. I'll say what I do and don't do. Graph g of x equals 2x squared plus 3. Compare the graph to f of x equals x squared. So I personally start with the shifting upward by going 3 up. 0, 3 will be my vertex right here. And then I do everything in relation to vertex as if it's the origin. From here, I'll go over 1 up, I guess in this case 2, and over 2 up 8, and things like that. 2 up from 3 is 5, 8 up from 3 is 11. That's because the vertical stretch factor of 2 is doubling the numbers 1 and 4. And that's where we get those. So if we're going to describe it, we'll talk about a vertical stretch by a factor of 2 and a translation 3 units upward. They probably mentioned some things that are different, that are the same, I should say, like the axis of symmetry. I'm going to keep those as they were. But notice that I did state translation last. Even if I do the translation first, I state it last, and that's important. I've stated that in the assignment videos as well. Because I know that I'm doing everything in relation to the vertex when I graph. That means everything is technically shifted up 3 on my accounts. Then I know what I'm doing. Okay, graph the function, compare the graph to f of x equals x squared. The question is that the last thing I copied? Yes, it is. So in that copy-paste job, let me do that one more time. Copy-paste job here, we're going to graph a couple of these. I actually feel like now, because they're vertical shifts, I need to probably use the taller graphs. So let me delete this one. Let me copy-paste the taller graph within here and see if it has the same scaling. Not quite. I need to probably make it... I just need to redraw f of x. My apologies. Let me, you know what? I'll just pause the video and do it. Well, actually, no, I won't. I'll talk through it if y'all don't mind. So in doing this one, again, regraphing f of x, now I can fit more points. Since you don't have numbers on here, keep in mind that there are little increments right there for 5, 10, and 15. That means the top of this graph reaches 17. So I can reach 4, 16 right here just fine. And I'm going to go ahead and have that on the other side because there's a reflection piece. So hopefully you saw how quickly I graphed that. Just, you know, without use of table, it's that I've done it before, but it's also that I understand the values that I'm squaring when I do it. And I'm going to be applying that same notion when we do everything else after that. All right, I want to get ready and copy this thing as I'm going to paste it in probably 3 other problems beyond this as we compare it to that graph. Let's go ahead and graph g of x equals x squared plus 5. Now to graph g of x equals x squared plus 5, how is it different from f of x equals x squared? The plus 5. We just go 5 units up, and it's going to be every bit the same as the previous problem. From here, 1, 1, 2, 4, 3, 9. 9 up from 5 is 14, and that's all I can fit, so let's do this on the other side. So the word isn't parallel, but this graph won't ever intersect as the curve has the same rates of change as the graph below it at those respective x values, but the y values are higher than those other ones before. So they'll never intersect. They'll never intersect. This g of x graph is simply just translated up 5 units from the f of x graph. So I'll write this bigger as I can fit a lot more. Translate g of x up 5 units. That's from f of x. That's the only transformation that's applied when it comes in comparison to f of x. And I'm probably understating it, but everything else would be the same without the vertex change, right? All right, that's number 6. Let's jump to number 7. H of x equals negative x squared minus 4. So there are a couple things going on there, and I'm probably, once again, glad that I have this whole tall graph to deal with. Yes, you. Let's move way over here. So this is h of x equals negative x squared minus 4. The minus 4 is a vertical translation 4 units downward. This negative x squared means negative 1x squared. That means no change in stretch factor, but it is flipped over. And technically flipping over is what we do first before we translate. Otherwise, I translate and to flip it over, that means it would go up here, and that's not what we're doing. I'm in relation to this vertex, but I am flipping over, so let's go 1, 1, 2, 4, and 3, 9 is all I can fit. What's 9 away from there? 18? Wait a second. Excuse me, that's a 4, huh? 13, excuse me. Boom, like that. So 1, 1, 2, 4, 3, 9 on the other side. So this graph is doing 2 things. It is translated, but before that, I'm going to mention it reflected over the x-axis. Right? Because what kind of happens first? This graph has to flip over first, and then it goes down 4 units. So the order does matter in how I state it. Even if I draw it backwards by translating first. Untease. Translate down for untease. Okay, that is h of x. We have g of x and h of x. Now time for m and n, numbers 8 and 9. Number 8. Are you ready? Another ax squared plus c. We have m of x equals negative 2x squared plus 6. So it is negative, it's flipped over, but, and it's stretched, but we start 6 up. We start the vertex at 0, 6, like that, and then we flip over. So we're going downwards, and we're going down twice as far. Not 1, 1, but 1, 2. Not 2, 4, but 2, 8. Not 3, 9, but 3, 18. 9 doubled. 18 down from 6 is Why don't I know that? Negative 8. Wait, negative 12. Right? 6, yes. Never was good at subtraction. And flip this over on the other side. So check this out. 2 away from the axis, 2 away. 3 away, 3 away. Very simple way of going about that. This is m of x. M of x. Make sure it still kind of looks like a U shape. I know it's tougher to do when it's a sharper graph like this. Just do the best you can, and definitely never make the graph go vertical. These are little characteristics, and always draw your arrows, stuff like that. These are small characteristics of these graphs that are sometimes lost, forgotten, ignored, not respected. Not disrespected, just not respected. All right, we have 3 things. Reflect m of x over the x-axis. Flip it over. Vertically stretch by a factor of 2. And translate 6 units upward. Okay, yeah, a lot of graph problems. When I said we have, what, 35 problems to do? Not even 10 in, so, you know. The graphs. Number 9. Maybe the last problem in section 3 too. Do not know. Gotta anticipate that. Number 9, n of x equals 1/3 x squared minus 5. So, let's go. N of x, and we're not done with these graphs. No. 1/3 x squared minus 5. So in the opposite sense, we are going to translate down 5 units, and we will be going upward, but it's not a stretch, it's a compression. 1/3 of our heights from before, we got to divide 1, 4, 9, 16, and stuff by 3. Now, if you're not as comfortable doing like 4 divided by 3, 16 divided by 3, I'll say them, I'll write them, but go for numbers that divide by 3. 3 squared, 6 squared, 9 squared, any of those that we can fit. I don't think I can fit 9 squared, but we'll try. Over 1 up 1/3. Over 2 up 4/3. 4 divided by 3 is 1 1/3. Over 3 up 9/3. 9/3 is 3. 1, 2, 3. So that's a perfect one. Over 4 up 16/3. 16/3 is 5 1/3. So now we're up here. Over 5 up 25/3. That's 8 1/3. 6, 7, 8 1/3. Over 6 up 6 squared is 36. Divided by 3 is 12. So this was 8, 9, 10, 11, 12. You can see where that's going. And I can plot all these points on the other side. I love these curves when it comes to that characteristic stuff. 49 over 7 up 49/3. 49/3 is 16 1/3. What was this? 12, 13, 14, 15, 16 1/3. And I don't think I can fit the 81/3, but I'm going to try and fit the next one. 64/3. That's 21 1/3 up from 5. That'll be 16 and wait, hold on. Did I say that right? 21/3. 21/3 from 5 is 16 1/3. Oh, 16 1/3 on y. That's right. This is 15. Here's 16 1/3 like that. So I'm just fitting a bunch of points. That's all I can fit. That's all. But imagine if you had to do this in the table realm. What you're calculating, what you have to plot afterward. I'm sure you couldn't do it with this speed like this, or understand what points to plot best to make it work. I'd want to say you'd want to plot numbers that are multiples of 3, because we can then divide those ones by 3. That's harder to tell when x is translated over. It's not in this problem, but if it was, it's harder to tell. That's why graphing without a table is great. If you know what you're doing, understand your graphs and functions, understand your numbers. So I'll always encourage it. I hope you do the same, if you're allowed. My students always allowed to, of course. That is n of x. Still a lot to plot there. Next time I'd probably just do the divisible by 3 stuff. So what are we doing for this? 2 things. We are vertically compressing, remember that begins it, by a factor of 1/3. And you are translating down 5 units. In comparison to f of x, that's what n of x is doing. Vertically compress n of x. Okay, that's the last one from that set. Let's see what we have coming next. Section 3.3. This is where everything gets this is where things get real. This is where you can have horizontal translations and such, and it's not so direct that that B term is just a horizontal translation, but it's a component that shows translation aspects. So before we start a problem, let's take a look at what they do for a problem in standard form. graph this guy, describe the domain and range. They're going to get heavy in this negative b over 2a stuff, and I suppose I'll follow it as long as we're in standard form. That's one of the unique things about standard form that we have outside of completing the square or factoring. We also have the y-intercept, and I'm sure they're going to talk about that. So the axis of symmetry, the x-axis is at negative b over 2a, 8 being our b value, and then a being 4. So 8 is b, 4 is a, or whatever, b is 8, a is 4. And negative b over 2a gets us the x value for the axis of symmetry, so, or the x equals equation. So that's also the x value for the vertex, and we can substitute negative 1 into the equation that we have here and find the y value of the vertex. A vertex is just a y value for a certain x, and we can know that x through negative b over 2a. So we're going to have to know what that is. So find and plot the vertex. When we plug in negative 1, we get negative 5 out, and so they plot the vertex here at negative 1, negative 5. Now from there, I'm privy to using the stretch factor personally. I'm going to use that. Stretch factor is 4, over 1 up 4, over 2 up 16, things like that if I can fit them. That being said, we also do have an extra point at hand, which is negative 1 as the y-intercept. In standard form, the c value is the y-intercept. They state that right here because c is negative 1, the y-intercept is negative 1. So that's a point that you can plot, and its axis of symmetry also has a point that reflects across that corresponds with it. If this is a point on the graph, so is this one that's 1 away. No different from what I've been doing. That's without using a table at all. Yes, we plugged in negative 1 to get the y value of the vertex, but that was a required bit, and we're building around negative 1 if you use a table the whole way. So they didn't really use a table. They only fit those points. I imagine that's almost all I could fit as well. They draw a smooth curve. They do talk about domain and range, so we'll be sure to do the same if they ask us to. Yep, they do. So we'll do all of that together. Let's go ahead and start off. Let's do number 10. On number 10, we are going to graph. By the way, we're not comparing to the f of x thing anymore, so I'm just going to go ahead and get this one individual graph on. So copy, paste, we'll get ready. In order to do this, we want to start first with the They say the whole axis of symmetry thing, so I'll describe that as well. Boom, boom. Axis of symmetry is x equals. We got negative b. That's b over 2a. That's a. You can't see it there. He's shy, but he's there. The opposite of negative 2 is 2. 2 over 2 is 1. That's the x value of the vertex. Now, as far as the vertex goes, the y value is found by plugging in 1 for x in this equation. So that's going to be 1 minus 2, which is negative 1, plus 7, which is 6. So your vertex is at 1, 6. So 1, 6 we go. Now from here, I can graph the rest. I'll plot this y-intercept value. The y-intercept value is at at 7 when x equals 0. That means there's a point across the axis of symmetry right here. Now, I want you to keep in mind, the axis of symmetry is on x equals 1. I'll draw it maybe this first time or a couple times. I won't do it each time. But this is now my axis of symmetry right there, that kind of orange line, if you can see it. So everything reflects across here. That's where everything's symmetrical. Now, does it make sense that the point 7, the 7 here is a y-intercept? Yes. This stretch factor is 1. So from this point, I'll go 1, 1. 2, 4, 3, 9, and I'll reflect those points across right there. That means that point's going to be hit. So 1, 1's here, 2, 4 is here, and 3, 9 is here. That's all I can fit on that side. On this side, I can go 2 away from the axis of symmetry and 2 away from there, 3 away from there, 3 away from there, and there's our graph. This is y equals x squared minus 2x plus 7. Now they want the domain and range as well, so I'm going to finish off with that. The domain will always be, for these ones outside of word problems, will be all real numbers. There's no restriction on x's I can plug in. It goes forever left and right. The range is limited by the vertex. Y in this case is greater than or equal to 6. 6 is the lowest value that we hit. It's the minimum, and there's that. All right, let's go to number 11, where I can possibly speed up on this stuff now. Number 11, unless the problem's just way different. Oh, it'll be a little different. We're going to be graphing y equals negative 3x squared plus 3x minus 4, or f of x. Now, they hate me, therefore they hate you, so they are going to be working off a different kind of vertex. The axis of symmetry is found at x equals negative b over 2a. That's negative 3 over 2 times negative 3. Here's where they hate you. That's negative 3 over negative 6, which is 1/2. I forget if I used to be putting the fraction 1/2 or the 0.5. I'll call it 1/2 for now. So fraction, x-axis of symmetry, that's no fun for me as well when I plot points because it's going to be halfway between values, but even more so if the y value is also a fraction, and I can only imagine it will be. So f of 1/2 is negative 3 times 1/2 squared plus 3 times 1/2 minus 4. That's a 4. So that's negative 3 times 1/4 plus 3/2 minus 4. Now, this is negative 3/4 plus 3/2 minus 4. You can imagine that you'd want a common denominator, but I've said this before and I'll say it again. When you're plugging in the x value of the vertex, the first two terms just takes this thing. You go 3/4 to the left and then 3/2 on the other side. Basically, here you end up with positive 3/4. Now, we still got to do minus 4. That's 16/4. And here we're getting negative 13/4. So as far as the vertex, I'm not any more of a fan of it than you are here. As far as the vertex, we have 1/2 for x and negative 13/4 for y. If you need to know those exact values, that's 0.5, right? And this is negative 3¼ so negative 3.25 for the y value. So the graphing here will not be fantastic, but we'll do with what we can, and we do have that y-intercept to work off of. So we start with 1/2 over and negative 3¼ down like that. Very ugly when it comes to what I want to plot. Now, I do have a y-intercept of negative 4, but that's not very helpful when it comes to this versus your axis of symmetry. Great. It's not like I can just draw the curve like that. I'm sure the book is going to say, no, that's fine. But I feel like I need some more points. So with the stretch factor of negative 3, only one more set of points I can really, truly fit that I want to fit. Over 1 down 3. And over 1 away from here, 1 away from there. Okay, I don't think I can fit... Can I fit 12? I can fit 12 down. Over 2 down 12 from here. This was negative 3¼ so 12 down from there is negative 15¼ Okay, I can fit that. So there's that one. Okay. I'm getting my graph taken care of. Yes, sir. Yes, sir. Yes, sir. Much more accurate from what we'd want to do, and we still have to write out the domain and range. Domain will be all real numbers, and this time we go downward when it comes to range. So domain's all real numbers, and the range, y is less than or equal to, what's the y value right here? Negative 13/4. Okay. All right, that was number 11. Let's go to number 12, the last one of that portion of the set. Y equals 1/2 x squared minus 6x plus 10. You might be turned off by that fraction here, but actually don't be. This one's going to be, maybe for the stretch factor you don't like it as much, but this one's not going to have a fraction x. Maybe it'll have a fraction y, but it won't have a fraction x. So y equals 1/2 x squared minus 6x plus 10. Let's check it out. The vertex axis of symmetry is at x equals negative b over 2a. 2 times 1/2 is 1. Opposite of negative 6 is positive 6. Bunch of things that are canceling themselves out. That's the x value for the axis of symmetry. Clean. The y value for the axis of symmetry is found by plugging 6 into here. I think this will be fine regarding fractions. 1/2 times 6 squared minus 6 times 6 plus 10. 6 squared is 36. Half of that is 18. 18 minus 36 is negative 18. Negative 18 plus 10 is negative 8. So we got a vertex at 6, negative 8. Easy plotting. Easy plotting. 6, negative 8. Now, this will run off the graph a little bit when it comes to, like, stretch factor's 1/2, so I'm going to be able to fit a lot on the left side. On the right side, I'm going to run out of room after 4 or so points plotted. So half of my heights, instead of 1, 1, it's 1, 1/2. Instead of 2, 4, it's 2, 2. Instead of 3, 9, it's 3, 4.5. And instead of 4, 16, it's 4, 8. And 8 up from negative 8 is 0. That's all I can fit on the right side. On the left side, I can keep going for a while. You know what else I can also hit is the y-intercept. And we should know the y-intercept of 10. Let's see if we actually hit it. 4, 8. Half of 25 is 12.5. 12.5 up from negative 8 is 4.5. Over 6 up half of 36, that's 18. 18 is 8 plus 10, and there is the 10 right there. 7 squared, 49. Half of 49 is 24 and a half. 24 and a half up from negative 8 is 16 and a half. That will just fit right here. So this graph may appear asymmetrical because my right side ran out of window range, but I promise it is not. It's just I can't fit it. And if I could, I would. I plot as many points as I can fit. That is my goal. That is my forte. So there it is. Left, right, arrows. Sometimes I'm not a fan of the appearance of asymmetrical graphs, even though they're actually symmetrical. Remember, we have an axis of symmetry. And it's right here at x equals 6. Way to go, you. That's number 12. About a third of the way through, unless they get harder. Let's look at number 13. The function f of t equals negative 16t squared plus 88t plus 12 represents the height in feet of a pumpkin t seconds after it is launched from a catapult. When does the pumpkin reach its maximum height? What is the maximum height of the pumpkin? So these are all vertex-based questions. We can use negative b over 2a to refer to it without any use of graph. So we'll go ahead and check that one out. Because it's a word problem, if there's a fraction sort of answer, I might instead use a decimal, so I might run to the calculator for that. So let's see what we got. The axis of, well, as far as the vertex goes, the when does it reach its maximum height? When? That's when the t value reaches maximum height. That's the axis of symmetry, t value. So t is negative b over 2a, which is negative 88 over negative 32, which is positive, well, you can divide them by 8 and you get 11/4, which is exactly, I said I'd write out a decimal, that's exactly 2.75, and I assume this is what, seconds? Pumpkin launch from a catapult, 2.75 seconds into it, that's what we get. Plugging that in, we can get the height. Max, what is the maximum height? Let's do f of 2.75 or f of 11/4, because I'm going to try this without a calculator. I'm going to work daringly. Negative 16 times 11/4 squared plus 88, it's not that daring, times 11/4 plus 12. Just, I don't know my decimal, I don't know what 88 times 2.75, actually I should. But okay, these numbers should be clean though with regard to like integers. So this is negative 16 times 121 over 16. Right, we squared the 11 and the 4. 88 divided by 4 is 22, and 22 times 11 is 242. And then plus 12. Now, negative 16 over 16 is negative 121, and negative 121 plus 242 is positive 121, and 121 plus 12 is 133. So I should get 133 feet for maximum height. There's when the maximum height occurs, what the maximum height is. And that's why I like word problems for those, to refer to those kinds of things, to really make sure you guys make sense of those. Keep in mind, this would have been an upside down graph. It's a negative 16t squared. So making sense of the when and the what for the x and y, or the t and f of t, are super crucial. Okay, let's go forward to section 3.4 on graphing vertex form. Vertex form means we can start right from that vertex to draw it. But they have some other questions up their sleeve, like odd, even, or neither. So let's begin with those ones. Let's start with the examples. The example, determine whether f of x equals 2x squared plus 4 is even, odd, or neither. Now, you may have learned with me, well, first of all, let's talk about to determine it. If something's an even function, that means that you get the same y value out when you plug in the opposite x. So if we literally plug in negative x into here, what happens? We square negative x, it becomes positive, x squared. So you restore, you get exactly what you had before. It was 2x squared before, it's still 2x squared now. F of negative x is the same thing as f of x, that means it is an even function. An odd function would occur if you get the exact opposite out, not just for one term, but all terms or all factors. Meaning if I can factor out a negative, I hope to get one of those to show you what it's like. And then a neither is if it's neither even nor odd. If it's not the exact same or the exact opposite. Now, what you might have learned with me is on polynomials, if every term is an even degree, that means I know it will be an even function. If every term's an odd degree, that means it'll be an odd function. And if there's a mix, that'll be neither. Only if you're looking at a polynomial. Written in standard form or simplified or whatever is where we would place that bet. So w of x equals 5 to the x power. Determine whether it's even, odd, or neither. This is not a polynomial, so I think it's worth testing what it looks like when we plug in w of negative x. This would be 5 to the negative x power, which doesn't turn it negative. It instead turns it into 1 over 5 to the x power. that may be some sort of inverse thing that we're looking at. Not truly. But it's definitely not the opposite in terms of negative for what this is. This is a case of neither, because it is neither f of x does not, f of negative x does not equal f of x or the opposite of f of x. So this is a neither case. Number 15, r of x equals negative 8x. Now it's a very quick calculation, but I can tell you, because that's of degree 1, and it's the only term in there being a monomial, that this will be an odd function. R of x is negative 8x. R of negative x is negative 8 times negative x. Negative times a negative is a positive. You get positive 8x. Positive 8x is the exact opposite of r of x, because this was negative 8x. This is positive 8x. R of negative x is opposite of r of x. That makes this an odd function, with every term being the exact opposite of what it was. This was the one where I wanted to get an odd function case, but I wanted multiple terms to display it. It doesn't look like I'll get that here. Then number 16, this is one where we have an odd degree term and an even degree term. I'm expecting a neither out of this polynomial as well. So no evens, looks like they'll show up except in the example. So it's good we had that example. But h of negative x, what's going to happen here is we get 3 times negative x squared minus 2 times negative x. When we square a negative, it'll turn positive, so this stays as 3x squared, but negative 2 times negative x is positive 2x. So here's what happens. This sign changed, this sign stayed the same, whereas this sign changed. If everything stays the same, it's even. If everything changes, it's odd. If it's neither everything changes or stays the same, it's a neither case, neither even nor odd. Now, we didn't graph those unless they asked us to. Nope. We didn't graph them. But symmetry for an even function is across the y-axis. Symmetry for an odd function is across the origin. You'd have to see what that looks like. And neither case is just neither symmetry for either. Like, this is not an even function. It's an even-powered function, but not an even function. All right, graph the function. Compare the graph to f of x equals x squared. We're bringing that back, so I might as well bring back the old parent function graphs like these ones here. So let me copy paste this whilst not bringing the blue. I can fit one on here. Oh, it didn't copy the graph. I'm for shame. I want the whole thing. Let's try that again. Let's just bring all that over and delete what I don't want. Oh, it's not bringing it. Not a fan. Not a fan. Let me just bring the curve. I'm lazy. I'd rather... There it is. Okay. Did it work? Let's see our points. Because the curve is my least favorite part in terms of drawing it. Doesn't look like it's right on. So let me fix this in a moment. Sorry about this. We'll accept that. Okay. Let's go to... Sorry about that, guys. Let's go to numbers 17 through 19, where we will graph the function written. In this case, h of x equals 2 times x minus 4 squared. We're comparing to that of the graph. So this is vertex form. Vertex form is f, because they didn't talk about it earlier. F of x is a times x minus h quantity squared plus k. This is a very classic kind of form that you'll be seeing quite often, not just for quadratics, but we saw it for absolute value functions. Kind of saw them in circle equations in a way. We'll see them for cubic functions, square root functions, log functions, trig functions, things like that in IM2. But a is still your vertical stretch factor as before, and with this perfect square factorization and this constant on the outside, h and k are your vertex. So your vertex is at h comma k. That's also why it's called vertex form. And so we can use those values to locate that and then use the stretch factors we need. We don't get the y-intercept this time, but that's okay. Your vertex for this problem is at 4, 0, which means it's a way we can describe this graph as well. So we get to shift this thing 4 things to the right. That's what I'll talk about. There's also a vertical stretch factor of 2 with a. So we'll go 1, 2, 2, 8, and 3, 18, which technically wouldn't fit, but I'll do my best to just kind of plot that on there. Okay, so this is the graph. It's still an upward facing guy. It's, believe it or not, skinnier. Sorry, this graph won't actually look very good. So it's a little skinnier of a graph than the black one, but we're going to describe it the way that I've been doing it before, how it compares. We vertically stretch by a factor of 2 and translate 4 units to the right. Now, this said x minus 4, yet it was a positive 4. Remember, the h is a flipped sign, whereas the k is same sign. There are reasons behind it, of which I'm not going to be getting too heavy into it. This is the review, and we're processing, working on problems on these. Plus, we're 45 minutes in, and just that, we're not even halfway through the problems. If 17 is half of 34, and we have 35 problems, time to keep moving forward. Number 18. Oh, I don't know if I got to paste things right. I just pasted the curve. I suppose I'll actually just redraw it. We got g of x equals 1/2 times x minus 1 quantity squared plus 1. You know, they never said to actually graph f of x. I'm just doing it for your sake. I don't know if you're supposed to regraph them as well. Here's the original f of x again, 1, 1, 2, 4, 3, 9, 4, 16. Yeah, it's what I call the 8-second graph. Did it take 8 seconds? It might have. Go back and time me. At least for 149, I'm sure I could. That extra 16 might have taken a little bit, plus I'm drawing the curve. Truly 8 seconds? Nah, it's okay. Okay, there's the original f of x graph. Keep that in mind. Let's just copy that guy. Boom. Great. Okay, let's go ahead and graph this guy. We have a vertex at 1, 1. H, K, opposite, same. Vertex is right here, where we also have that f of x point. And then 1/2 is our stretch factor. 1, 1/2, 2, 2. Half of 9 is 4.5. Half of 16 is 8. 8 up from 1 is 9. And half of 25 is 12.5. 9, 10, 11, 12.5. Flip them over this new axis of symmetry that we'd be referring to at x equals 1. Hey, it hits that point. I forget if this, it might have had it. I forget if we had systems of equations on this. I think that's in chapter 4 where we're going to have systems of equations. But from this set here, we found the points of intersection. Points of intersection are there and there. I know they didn't ask for them, but I'm telling you that stuff would be relevant in a future kind of section. Okay, so how do we compare the two? Besides where they intersect, we do vertically compress by a factor of 1/2. And we translate 1 unit right and 1 unit up. There it is. Okay. Number 19, last one graph from this set. Unless I got to do some more on the bottom. Let's do q of x equals negative quantity x plus 4 quantity squared plus 7. Hey, it doesn't seem to copy two things at once anymore. It's like it lost its ability to do so. Or maybe I didn't give it a chance to. Maybe it has to copy the clipboard. Okay, it's not copying the graphs anymore, so I don't know. I guess I have to redraw. If you don't mind for this one, guys, I am just simply going to copy. I'm just going to draw a graph because it doesn't seem to lock those in. I'll keep trying later, but redrawing that first one over and over is kind of damaging to my core. All right, I got a vertex at negative 4, 7 this time. The h, x plus, that's the opposite of minus, right? Minus a negative. So negative 4, 7 is this vertex. I kind of wish I had that graph for reference. And then just a negative 1 for a. That just means it flips over. No stretch. It's just got the 1, 1 vibe. 1, 1, 2, 4, 3, 9, and 4, 16. 16 down from 7 is negative 9. 5, 25. What's 25 away from down from 7? That's 18. That technically doesn't fit. It'd be 1 away, but I can force it. So we'll go ahead and do that. Much faster than a table. Much faster than a table. Never a doubt. Never a doubt. Okay, and there is our curve for this guy. I know I didn't plot the f of x. My bad. I'll still describe the changes to it. You take the original f of x graph that would have faced up like that. We're going to do three things to it. We are going to reflect it over the x-axis. Then we're going to translate 4 units left and 7 units up. Remember, there is no vertical stretch or compression on this, just the reflection. There, A is still affecting it, but just through a reflection. Okay, number 20. Consider the function g, oh, it says graph. Okay, we do have to do another graph. Consider the function g of x equals negative 3 times x plus 2 quantity squared minus 4. Graph h of x equals g of x minus 1. So for number 20, you kind of have two options here on what you're going to do. But I start with this graph here. Negative 3 times, or this equation, this function. Now, there's h of x equals g of x minus 1. Okay. In an equation sense, actually, let's start with the graph, and then we'll have the equation go to it and say, see, it's the same thing. In a graph sense, h of x is g of x minus 1. That means that h takes this graph here and translates, remember, just like the vertex was that minus 1 here, where we would go 1, like for vertex is 1, 0 or something like that. This would take everything and move it 1 to the right. So for h of x, you're going to translate g of x 1 unit right. Take g of x's graph, just move it over 1. So if I take the original g of x graph here, I have x plus 2 quantity squared minus 4. That vertex is at negative 2, negative 4, and then the a value being negative 3 means there's a flip over. So we'll go negative 2, negative 4 here. Looks like I'm not going to be able to plot many points. I'll go 1 over 1 down 3. Over 2, can I fit down 12? Yeah, I think it's at negative 16, so I can fit a little bit. Here's the original h of x graph. Okay, I'll mark that. I'll note that that is kind of a blue graph because I'm going to have another one that's kind of literally right next to it. So there's that graph. Now, from there, we have our h of x graph. It takes the g of x graph with the x minus 1, and everything is going to be 1 unit over. So instead, if I kind of copy paste this, not kind of, but if I, well, I guess kind of, copy paste, let's change its color, make it like green. We're going to take this graph and move it 1 unit over. I know you might have to do the redraw of all these points, but I'm just giving you that right idea. So that's this graph. That's what h of x looks like. Now, if you're not convinced by that, let's do this. Let's take h of x by being g of x minus 1. That means for g of x minus 1, we are going to substitute x minus 1 anywhere we see x in this equation. This becomes, x, instead of x right here, this will be x minus 1, and they're still at plus 2, quantity squared minus 4. That becomes negative 3 times, what's negative 1 plus 2? Positive 1. So this becomes an x plus 1 inside of there, squared minus 4. That's what g of x minus 1 looks like, which is the same as h of x. That means this is h of x equals. Now here's another version of the equation. What do you see? What we see is the vertex is at negative 1, negative 4. The a value is still negative 3. Is this vertex at negative 1, negative 4? Yes. So could have I manipulated the equation to get this one to then grab that information? Yes. This one is just telling you, you take these things to the equation and do these to it. They apply the same way as the quadratic function does. So if there was a 5 out of here, and if there was a plus 9 right here, what would I do? I'd vertically stretch by a factor of 5. I'd translate 1 unit right, 9 units up. But I'd take the blue graph and do all those things. So they're not doing that, but that's what we would do, and that's how they would affect the equation. So I wouldn't say a tricky problem, but a very conversation-heavy problem on how you can go about doing the information there. All right, let's go to number 21. Write a quadratic function whose graph has a vertex of 3, 2 and passes through the point 4, 7. And they're probably imagining do it without a graph. But you have the vertex of 3, 2 through 4, 7. What they really want you to do, and I could use the graph to support this, but what they really do want you to do is come up with the stretch factor that'll make this happen. We know that the equation can be written in vertex form, so we have hk, but this is some xy on here. We don't know a. We don't know a. So we have an equation where generally would look like this form. We can substitute all of these values into here. I'm actually going to begin though with just y equals a times x minus 3 quantity squared plus 2. This is my h and k. What I want to kind of emphasize is these will stay firm in place no matter what I do. These are the mainstays of my equation. X and y are generally a part of your equation for your entirety of the graph. This just happens to be one solution that we can use so we can discover a. So these are mainstays, this minus 3 plus 2 for the final equation. I just need to find a. To find a, let's substitute. I'll just use black. To find a, let's substitute 4 for x and 7 for y in this equation. So we'll have 7 equals a times 4 minus 3 quantity squared plus 2. Or 7 equals a times 4 minus 3 is 1. 1 squared is 1. So, 1 plus 2. 1 times a is a, and subtract 2 over, you actually get 5 for a. So a equals 5. So my equation will now actually just look like y equals 5 times x minus 3 quantity squared plus 2. Yes, those x's and y's are back, so we can use this for the entirety of its graph. Now, if I used these and plotted points on these for a graph, like here's 3, 2 for the vertex, and here's 4, 7 for this point, that means that, we got a quadratic that looks like that. So I can just work off of how far away is this? This is over 1 from 3 to 4 and up 5 from there. That doesn't make it a slope, but a quadratic would normally go 1, 1. So to go 1, 5 means it's 5 times higher than it was before. That makes the a value 5. So I could have discovered it by other means, and I often do, especially if they give you the graph. But if you make your own, I guess that'll work too. All right, let's move on to section 3.5, where we have intercept form. I apologize if I ever call it factored form, but as you can tell, these are clearly factors, with a being a common factor here. Now, a represents what it's always represented. A is the vertical stretch factor, the reflection component, all that kind of stuff. But in factored form, as you wouldn't be aware yet through chapter 3, these represent the x-intercepts of your equation. That means these are the places where we cross the x-axis. But you wouldn't know in any other way for what these things are, but these are the x-intercepts. Once you hit chapter 4, you get heavy into the whole zero product property of it all. We'll leave that for chapter 4. But here we're going to, in the example graph, f of x equals negative x plus 4 times x minus 2, describe the domain and range. First of all, the a value is a negative 1. That's, if in terms of replacing what we're seeing there, that's the a value. That means it's going to flip over. No stretch, but flip over. X plus 4, opposite of, the minus p, that means we got negative 4 as a value. That's one of your x-intercepts. The other one, x minus 2, that means 2 is one of your x-intercepts. So we actually begin by plotting negative 4, 0, and 2, 0 on there, because these are actually the same distance from the axis of symmetry. X-intercepts are at the same height, so they're the same distance from the axis. And what we're going to do next is find the axis of symmetry. You can either do it on the graph by counting half the distance between negative 4 and 2. They're both 3 away from each other, and you can find that negative 1 value. Or you can mathematically do this by calculating the average of those two numbers. A midpoint is an average as well. So average negative 4 and 2, add them up, divide by 2, you get negative 1. That's the axis of symmetry, also the x value of your vertex. If that's the x value of the vertex, you can find the y value by plugging in negative 1 into your equation, and we can use the factored form version, which may be kind of nicer than standard form sometimes. And you apparently get a value of 9 out, therefore your vertex is at negative 1, 9, and you got a bunch of points that were hit. If you want to find more using your stretch factor of negative 1, go ahead and do it, but you'll notice that they should at least happen to hit the x-axis, the x-intercepts here when they're graphed. So we'll go and do the same thing. They do have domain. They state all real number domain. Range is y is less than or equal to 9 because that's a maximum. And those are the same things from before. So let's go ahead and check these ones out. Oh, before we do, there's a part B. Different kind of question. Use the zeros to graph h of x equals x squared minus 7x plus 6. So in this question, there is, I guess it's use of, because I haven't done these in a while. I forget which things we do and don't know. But we do work on factoring. Use zeros to graph. It's in standard form. It opens here. So plot this polynomial. I'm trying to remember. So we already factored. I take it back. Did we already solve factoring in chapter 2? I'm forgetful where we are when it comes to our chapters. Full disclosure, guys, this is recorded out of order. Check this date. I'm in May. of 2024. The previous ones I recorded were probably back in October of 2023. So I was thinking that was in chapter 4 when we solved by factoring. We might have solved by factoring in chapter 2. So you probably fully know what zero product property is when I brought it up. My bad. My bad. Because I just saw, hey, they factored this. Were we supposed to know how to do that? Yeah. So x squared minus 7x plus 6, two numbers that multiply to 6 and add to negative 7 are negative 6 and negative 1. By zero product property, the x-intercepts are 1 and 6, so we can plot them here. And then I guess they do the same thing as before. Draw a parabola through by finding the axis of symmetry and everything else like that. You average your points to count half the distance in between. It looks to be a fraction. So get ready for probably having something like that on our problem set. All right, let's go ahead and take a look at some of those problems now. Let's look at numbers 22 to 24, where we have a factored form thing. We will graph the function, label vertex, axis of symmetry, and x-intercepts. So I will be drawing axis of symmetry. I should, because it's half the distance between these values. And then describe the domain and range. So let's do the tall graphs. It seems that that's the popular one here on out, at least until we do sideways parabolas, and I think that's in the next section. Oh, that's what the next section was, focus and directrix. That's right. Okay. All right, so number 22, we have y equals x minus 4 times x plus 2. I really tried to pass this off as I was recording this at the same time as the others. It didn't work. It didn't work. I should have remembered what we had before. Okay, first of all, the a value is 1. Just keep that in mind when it comes to the graph stuff we'll do later. But when it comes to x-intercepts, we have x-intercepts of 4 and negative 2. Now, if I plot those, 4 and negative 2 are right here. If I wanted to find half the distance between, I could tell you they're both 6 apart from each other. So half that distance is 3, and 3 apart from 4 is 1 to the left. Halfway, 3 away from negative 2 is also 1. So the axis of symmetry labeled is there at x equals 1. That's the AOS. Now, if we want to find that ourselves, we can go ahead and calculate that by getting the average of 4 and negative 2. 4 plus negative 2 divided by 2. That's 2 over 2, which is 1. So that's the other way of getting it. I'll probably use the visuals as long as they're making me graph anyway. But we still got to plug 1 into our equation to get the y value of the vertex. We have to figure out where it hits. So this will be at 1 minus 4 times 1 plus 2. 1 minus 4 is negative 3. 1 plus 2 is positive 3. You will see backwards effects on these when you're plugging in these values for the vertex, and we get negative 9. So the x value is 1, the y value is negative 9. That is the vertex at 1, negative 9. Let's label it as they ask us to, right there. Now let's plot the rest of the points on this graph. The a value was 1, so I should go 1, 1, 2, 4. 3, 9 is already hit. Let's just confirm it's there. Awesome. I got a few more up my sleeve. 4, 16. And 5, 25 I think should be hit. 5 away from that is 16. Yes. Yes, yes. Right there. Okay. There's the graph. I believe I have my labels because I have, well, I didn't label them, but I have those points. So they said label, I think, the x-intercepts, axis of symmetry, and vertex. Can't really label axis of symmetry as far as like circling them, but here's the vertex. Here are the x-intercepts. That's a V, by the way. And there's the AOS. Domain and range. There's one problem. Domain, all real numbers. Range, y is greater than or equal to negative 9. I should probably box those. Okay. Let's go to number 23. Let's graph f of x equals negative 3 times x plus 3 times x plus 1. Also a factored form set. So if you shouldn't be, you might be new to my videos, but you shouldn't be new to this material. If you're understanding that we've done standard form, vertex form, and now factored or intercept form, all of them have their advantages and their differences in what they do. And you can go from one to the other. I believe we actually have to go from one to the other in a bit, from standard to factored. But we can also go from factored to standard clearly just by foiling and distributing everything out. So they all have their uses. Depends on what you have. If you're in the form, you probably might as well do some graphing from it if you want to. So the x-intercepts are going to be negative 3 and negative 1. When it comes to that graph, negative 3 is here, negative 1's here. Halfway in between is indeed negative 2. I'm not going to calculate that. I'm just going to draw and label it. So axis of symmetry is at x equals negative 2. Now, if x equals -2 is that value, -2 is what I will be substituting into this. I believe I will get 3 as my number. But when I plug -2 into here, I get, remember that's the x value for the axis of symmetry. So here I will get -3 times +1 times -1, which is +3. So your vertex is at -2, 3. That's this point right here in blue. And the stretch factor of -3 can kind of confirm that we're going the right way. Over 1 down 3. And then over 2 down 12. And I think that's all I'm going to be able to fit. I can't go over 3 down 27. No way. So let's just fit those and be all good with that, with the labeling of the x-intercepts and the vertex. The domain is all real numbers. That's not new. The range, why do I have a colon there? The range, little bit new. Y is less than or equal to 3. Once I erase the colon and write a comma. A symbol typo. Y is less than or equal to 3. There's number 23. Another one of these. Number 24. Number 24, y equals x squared minus 8x plus 15. Okay, this one is in standard form. They say graph the function. They don't say what to do with it, but if it's factorable, we might as well try and factor it. So, and it is factorable. Y equals x squared minus 8x plus 15. Now, what's interesting is they say use zeros to graph the function for numbers 25 to 27. This feels like the kind of question that I would do this with. I don't really know what the difference is between the question I'm about to do and the ones later. I'll do what I can. By the way, this is the y-intercept of the graph. I can use that one in a bit, but I'm still going to go ahead and factor this thing. We are out of factored form, intercept form problems, by the way. So this is x minus 5 times x minus 3 as far as factoring goes. So we're in the form. The x-intercepts are 5 and 3. And halfway between that is 4. So I'm not going to pretend like that's difficult to figure out or that I need to average that, calculate that through averages, so I won't. So 3 and 5 are the two x-intercepts. I can label those in a bit. Got the axis of symmetry brewing right about there at x equals 4. 4 is what I must substitute. I don't know why I said it that way. 4 is what I must substitute in for x to find the y value of the vertex. So y is 4 squared minus 8 times 4 plus 15. That's 16 minus 32, negative 16, plus 15, which is negative 1. So my vertex is at 4, negative 1. So with a vertex at 4, negative 1, stretch factor of positive 1, and by the way, a y-intercept of 15, therefore a reflected point, 1, 2, 3, 4, 1, 2, 3, 4 away. This should all make sense. 1, 1, 2, 4. 3, 9, and there's our 4, 16 on those ones. So there's the graph. Let's get the labels. Let's get domain and range, and let's get out of here with that set. I am confused as to how the next set of problems work outside of we don't label and say domain and range, but that's the vertex. These are the x-intercepts, and then that is the that's the axis of symmetry. Okay. Oh, domain and range. Domain, all real numbers. Range, y is greater than or equal to negative 1. That's the minimum. Okay. Numbers 25 to 27 use zeros to graph the function. This is where I don't get what the difference is between this and the other. See, they didn't spend a lot of time plotting the average stuff. Maybe we're just allowed to not actually find that vertex. Maybe we're still allowed to not find the vertex. Maybe they're allowed to be rough graphs. I'm going to do rough sketch graphs. I'm not even going to use graph paper. That's right. They don't seem to be doing anything with those, so I'm not going to. This seems like a lesser than problem. Y equals negative 2x squared plus 6x plus 8. So this one's also factorable, I'd imagine, but we start with the greatest common factor of negative 2. And that is kind of important when it comes to this form, right? There's an a value that's outside of there that references the stretch factor, and it sticks outside of there as you do the other factoring. So this factors into x minus 4 times x plus 1. And they say use the zero, so I'm just going to work off that zero product property if you forget what it is. Set this equal to 0. This is why when x minus 4 equals 0 or x plus 1 equals 0, that x equals 4 or x equals negative 1 are the x-intercepts. So the x-intercepts are, in zero product property, the values of y when x equals 0. That's what we can plot. And I'm probably glad that I might not be forced to do the whole graph everything kind of thing. But we do have 4 and negative 1. Wait, is this an upside down graph? I think it is. We have 4 and negative 1 as these x-intercept values. Now, it is a negative stretch factor, and it's stretched, taller. 8 is the y-intercept. I want to show that one as well. So here's 8, and that would mean that there's a point that also goes across there. So this graph is some downward bit that does this and comes back on the other side and does that. Oh, I'm graphing it basic. If they didn't say anything, if the example didn't do the vertex stuff, neither am I. Because that would have been a fraction vertex value. And you know what? We've gone over an hour 11 right now, so I have the right to be selfish. Draw the graph as you need to. Use a table. Use the stretch factor. Number 26. F of x equals x squared plus x minus 2. But yeah, no doubt. I don't know how these problems are meant to be treated differently from the other ones there. This is all about factored form or vertex form, so x plus 2 times x minus 1, I want to write factored form out of it. When you set things equal to 0, x is negative 2 and 1 as the zeros. So those are the zeros. That means those are the x-intercepts. So let's do it again. So we have negative 2. Well, hold on. This is the y-intercept. So negative 2 and 1. As these guys here, negative 2 is the y-intercept. Now, that doesn't mean that's the vertex, right? In fact, that's not symmetrical otherwise. See, these have axes of symmetry at decimals, at fractions, like half values. So probably not too fun, but it's going to kind of, let's see that again. It's going to kind of come down, maybe like that, and then come back up through there. So the vertex isn't on negative 2. It's a little bit left of it. I think at negative 1/2. At negative 1/2 it would be. There's that graph. One more of those, number 27. We have f of x equals 2x squared minus 18. Looks a little unconventional to begin with, and actually we should be able to do this. See, this is where people get stuck in their ways of a certain kind of thing that they do. You learned something before, and this is the same video that we did section 3.2 on with the review. That was ax squared plus c. Well, guess what? This is ax squared plus c. I just graphed those functions before, and I did, by the way, standard form graphs where I could have used negative b over 2a instead of factoring. But, who's stopped me from graphing right here? I can just start at 0, negative 18, and a stretch factor of 2, and boom, I'm done. Which is exactly what this is. But we're practicing factored form, so you should practice it, but at the same time, don't just marry yourself to it just because that's what you last practiced. But for the sake of this review, we will. So common factor of 2 would make 2 our a value, and this is a difference of 2 squares here that can factor into x minus 3 times x plus 3. Therefore, the zeros are x equals 3 and x equals negative 3. Those are the x-intercepts. So when it comes to graphing, we do have 3 and negative 3 as the x-intercept values. And negative 18 is the y-intercept. I never stopped short in saying that it wasn't the y-intercept, but it also happens to be the vertex. That's the thing that's special about that one. Negative 18. This graph is symmetrical across the y-axis. It is an even function after all. And this thing is going up and through like that, where you go over 1 up 2, over 2 up 8, and over 3 up 18, where it hits the x-axis. All right, that's number 27, at least with rough sketch graphs. I apologize if that's not what I was supposed to do, but I think it makes a little sense to do it. Number 28, last one in this section on 3.5. Write a quadratic function in standard form whose graph passes through 4, 0, and 6, 0. Now, it says write a quadratic function. It is open-ended, which means that we can do more than one because it all depends on a. Now, a is not any one known number, but because 4, 0 is used, we can have x minus 4 as a factor. Because 6, 0 is used, x minus 6 can be a factor. So a can be any number under the sun that we'd like. I'll make one up. Let's use negative 4. Negative 4 times x minus 4 times x minus 6. Listen, most of you guys can use x equals 1, and you're good. And if you just use x equals 1 in standard form, when I FOIL this thing, it'll say x squared minus 6x minus 4x plus 24. And you'd be good with this part right here. No negative 4, no parentheses, all that. But I'll distribute the negative 4 in mine, and I get negative 4x squared plus 40x minus 96. And that is a quadratic equation in standard form that passes through those things because those factors in zero product property lend to those x-intercepts, lend to those zeros. That's going from factored form to standard form. That's the last one in that section. Okay, yes, focus and directrix of a parabola. I don't want to make mistakes. I know how to do it. I don't want to make mistakes on the things that we talked about at the time. So let's see what the examples lead us to, and then I'll work based off that. Like what letter we use for, we use P. In the past, I know I've used C before, but this book uses P. Identify the focus, directrix, and axis of symmetry of 8x equals y squared. Graph the equation. First of all, it's good to get the single degree variable by itself. In this case, it's going to be x, making it an x equals equation. An x equals equation means the graph is going to be going either to the right or to the left. Because it's a positive y squared, it'll be going to the right. Something to keep in mind. It's going to be just like the graphs of before, where y equals x squared, only now instead of 1, 1, 2, 4, 3, 9, it's 1, 1, 2, 4, 3, 9. Like that. It's actually a sideways parabola. Identify the focus, directrix, and axis of symmetry. Now, for me, this is where I'm going to defer a little bit. I use the equations a equals 1 over 4p and p equals 1 over 4a separately from the material, meaning separately from the equation. So I can then solve and find my thing. P is the distance from your vertex to your focus of your parabola in the direction it's supposed to go. In a rightward facing graph, such as this one right here, the focus would be inside the parabola to the right. If P is 2, it's 2 units inward from the here. The directrix is a line that goes on the other side of your parabola. It's vertical for a sideways facing parabola. It is horizontal for an upright facing or downward facing parabola. So this could be focus and directrix, focus and directrix. Focus is a line, directrix is a line, focus like the vertex is a point. It's a point. And P is the distance between them. We can use it we can find it with A. So 1 over 4p y squared is how they say that. This p value happens to be 2 if you set it up that way. So the focus is 2 away from the vertex. If the origin is at 0, 0, this focus is at 2, 0, 2 away from there. The directrix is 2 units in the other direction, so x equals negative 2. So we can see right here, vertex at the origin, 2 units away here is is your focus. 2 units here is the start of your directrix where you can draw your line. Now, what the focus and directrix are, they are points from any point on a parabola that are the same distance away if you find the two shortest distances, such as this point is the same distance away here as it is there. These are both congruent to each other like that. Or this is congruent to that. And I think you can tell those are the same. Those are units of 4 away. So drawing a parabola with those things in mind, we're not going to make that whole spider leg looking thing, but we are still going to construct the parabola with focus and directrix, and all is good. They said use a table of values. I ain't using a table of values. Part B, write an equation of the parabola shown. This is where if you're given some information from a graph or what have you, we can find the distance between focus and directrix, call it P. We can use that P value to come up with an A because A is 1 over 4P. And then we can use the HK that we have for the vertex. This is at 2, 3 for that vertex. That's HK. And establish that it's a y equals x squared equation because it's an upward facing parabola. So if the A value is going to be apparently 1/4 when you use the 1 over 4P, we can say y equals 1/4 times this x minus 2 quantity squared plus 3. Remember, it is a y equals equation. That's the example. I said it really fast, but I'm going to do some of my own, I'm sure, when they give me questions. Looks like I have 4 to do total. And I hope I get one where I get to do any of those things. So let's start this thing off. Let's go to number 29. And oh, by the way, if I have to do my own graphs this time, I think I'm going to use the more square scaled face appearance of a graph like this because of sideways facing parabolas. I want to give them their due. Unless they go off the graph very poorly. So let's see what happens. Number 29. You can make a they start with a word problem. You can make a solar hot dog cooker by shaping foil-lined cardboard into a parabolic trough and passing a wire through the focus of each end piece. Yeah, oh, the drawing. Okay, so that right there. For the trough shown, how far from the bottom should the wire be placed? I assume they mean that points the focus. Let me read that again. You can make a solar hot dog cooker by shaping foil-lined cardboard into a parabolic. So here's the parabolic trough. I assume this is supposed to see, they're not coming out and saying it. But I guess that's supposed to be the focus. For the trough shown, how far from the bottom should the wire be placed? Wait. You can make solar hot dog by shaping. Never mind. Maybe the hot dog thing has nothing to do with it. Cardboard into parabolic trough. Passing a wire through the focus. Oh, through the focus. I totally didn't read that. Okay, got it. How far from the bottom should the wire be? Okay, so let's just do stuff with this. Let's do stuff with this. Now, with this one here, they didn't really give us where it's placed, the vertex of this thing, so I can kind of makeshift that, place it at the origin, and go from there. Now, they didn't really give us points. They gave us heights and distances, so we can come up with things based off that. Here's what I don't get. This says 4 inches, but this shows 4 inches off the ground, and I don't know how far off this one that this vertex is supposed to be placed at, unless that's supposed to be the directrix. Perhaps it's supposed to be the directrix to talk about a distance from here being 4 inches and saying to be congruent here from 4 inches, a point on here should be the same distance as a point from here. So if those should be the same, and that's 12 inches far out, boy, there's a lot on this problem. There's a lot on this problem. So if this is 4 inches away, that doesn't tell you that the directrix is 2 up or 2 down. This is a lot of stuff. So, okay, check this out. The 12 inches, let's start with that. 12 inches means from -6 to +6, period. How high up or down is that 12 inches? I don't yet know. But when I have my parabola and it hits those points, this is a basic nature of it. This isn't exact. So there's the 12 inches across. That means that this is 6 inches here. That means that there's a point on here that's some 6, y. I need the distance from here to be the same as the distance to my directrix. The directrix is 4 inches. I'm discovering this as you are. That means this has to be 4 inches as well. Now, they didn't teach you all that in these sets of problems. This is kind of above and beyond for review if that's what they're talking about. I can't really follow all this stuff. But in order to do this, I'm going to do this to figure out what my equation is, to then figure out what my stretch factor is, to then figure out what P is, to figure out where my focus is. So I need this distance here, 6 squared plus y squared to equal 4 squared. This is 6, this is y, that's 4. So I need 6 squared plus y squared to equal 4 squared. I hope I'm envisioning this problem correctly. How can 6 squared plus y squared equals 4 squared? That doesn't make any sense at all. Y can't be, it could be a negative number, but it's not. Oh, that's the focus. I take that back. That's not distance to vertex. That's distance to focus. Hold on. Let's do some of that again. Maybe that actually helped me find the focus point and I don't need to figure out the whole equation. So my focus is some point here, which is at some 0, p. And the distance from there to here is 4 inches, as it is to the directrix. That's also 4 inches. So instead, the distance from p to y is y minus p. So this is going to be 6 over. This is going to be y minus p up, and that's 4 across. So I have a right triangle where I have, let me just redraw it again so you see it. This is 6 over y minus p up, and this is 4 over there. Wait, that still doesn't make sense. Huh. I think I got to pause and think about this problem. I think I'm misconstruing what it is that I'm seeing here, especially on this dotted line. Let me think about this for a moment. Okay, so I've made an executive decision. because of the impossibility of the thing that I have going on there. And I said, this problem's struggling itself. Not only can you have a width longer than hypotenuse and that kind of stuff. My executive decision here is that this part, what do they call it? The trough? That 4 inches is the bottom of the trough thing. I don't know if that's true or not, but like from here to here, for example, would also be 4 inches. It doesn't look like that's what we're doing. It looks like this is like on the bottom, like I'm kind of seeing it as like the bottom leg or something up to there. But, and then I was saying like, oh, that's directrix stuff. I don't think that's what they're talking about. Number one, that would make a very complex problem for it. And number two, I don't know. That's just the executive decision I'm going to make on this problem. So I'm going to work off it like that. So here's what I'm going to say instead. Same concept with what I just said before. Vertex is here, but the vertex is like this guy. But because that thing is 12 inches across, that you get 6 inches over, where you also go 4 inches up like that. So there's a point on this parabola that should be 6 over and 4 up right here as the parabola goes. And clearly then that means negative 6, 4 as well, right? There's also negative 6, 4. But we have to come up with what this equation is. Not so hard now. Come up with this equation is. So with that equation, you can get the A value. Then you can get P. Then you can get the focus, things like that. So what graph starts at the origin and has that kind of stuff there? Well, keep in mind, normally, because here's how I do the stuff, right? Normally, with the A value, you would be, how do I say it? Normally, when you square your X value, you get a certain number, right? So when I square 6, I should be getting 36 on here. But now when I'm multiplying 36 by my A value, I'm now getting 4 instead of 36. So A is 4 over 36, which is 1/9. Normally I don't write that out, but I say, instead of going over 6 up 36, I'm going over 6 up 4. I'm going up only 1/9 of 36, and that's how I'm working that out. So A is 1/9. As far as my equation, it's y equals 1/9 x squared. But as far as using this A value, I have to get P out from that. If A equals 1 over 4P, and A is 1/9, I get 1/9 is 1 over 4P. Cross multiply, 4P is 9. Divide by 4P is 9/4. That's also 2 1/4. It's also 2.25. And I don't know which one I prefer using right now, but that's the P value. That's the distance from my vertex to my focus, my vertex to my directrix, being a y equals positive x squared equation. My focus is inside this way. My directrix is outside that way. Now, what do I need? How far from the bottom should the wire be placed? If it's the bottom of the trough, and they're talking about the wire from the hot dog, so I'm guessing that bottom of the thing is the same as the bottom of the stand, and my eyes just deceive me because there's a shadow underneath there, and the 4 clearly goes to that shadow. Anyway, how far? 2.25 from the bottom should be the focus. 1, 2, 2.25. Here's your focus at 0, 2.25. So I don't know if I explained it great. The problem is they kind of started us off with this problem. The real problem was the drawing. But the focus is 2 at 0.25 inches from the bottom, from the vertex, from the bottom trough part of the aluminum foil of the hot dog cooker thing, if that's what we're saying. So my final answer there is going to say 2.25 inches. I don't know if that's right, because I don't know if that's how they wanted the problem to be interpreted. But, man, I'm going with it. That drawing's a little screwy. I had to make a decision. The other stuff was not operating with me. I'm going for it. Not living on that problem for too long for something that should probably have a better drawing. Number 30, graph the equation 36y equals x squared. All right, now you're talking my language. Identify the focus, directrix, and axis of symmetry. So a little more standard. 36y equals x squared. Clearly, y is the one we can get by itself if I divide both sides by 36. I get 1 over 36x squared. That's a weird thing to graph, but the focus and directrix will at least probably be cleaner numbers. Whenever this thing's more of a fraction, because the p has like a inverse relationship with a, then generally once a gets smaller, p gets bigger. Once a becomes a fraction, p kind of often doesn't become a fraction. But 1 over 36x squared. Now, there are a lot I won't be able to plot very well. Like over 1 up 136, over 2 up 436, 1/9, not really. can pretend like you got something there. Over 3 up 936. Well, at least that's a quarter. At least I can kind of fit that. Over 4 up 1636. I don't even know that fraction. 2536, no. But 6 up 36 over 36, that's 1. So we go a quarter of the way up when we're 3 over. We go 1 up when we're 6 over. Seems like every 3 we can get something else substantial. What's 9 over? Oh, 81 over 36. What's that? 2 and a quarter. Not great. Over 9 up 2 and a quarter. But I think that's the next most substantial thing I can find. So as far as this graph goes, it's looking very wide. A little too much character for my blood. But this thing's looking like that. And I seem to recall us having some graphs like this. I don't know if they've ever been that stretched out. But boy, is that one stretched out. So there's that. We need to find the focus and the directrix. We got to find basically P. And then go P units up from the vertex, P units down from the vertex to find those. So, identify the focus, directrix, and axis of symmetry. So, A is 1 over 36. A is also 1 over 4P. So, cross multiply and divide by 4. You get P equals 9. Now, if P equals 9, we get to go 9 units up from here, 0, 0. That's at 0, 9. That's your focus, 0, 9. For that point, the directrix is 9 units down, and this horizontal line that goes across, the directrix is the line y equals -9. That's how that works. What else did they want? The axis of symmetry. I probably should have been drawing that first. This orange line going away, the axis of symmetry is at x equals 0. I have to sneeze, I think. Okay. That's number 30. Two more questions in the set, and we still have another section, but I guess 3 more questions in the last section. Number 31. Sorry. Okay, number 31. Write an equation of the parabola with the given characteristics. We got a vertex at 0, 0, and a directrix at x equals 2. So for this one, you know, let's get the graph to start it off, just to kind of see what we're doing. Vertex is at 0, 0. Directrix is at x equals 2. Means the parabola opens up away from the vertex. Parabola is going to open up this way. This is a rough sketch version of the graph. I don't care exactly what it is, but I'm going to get some semblance of it. So it's opening up that way. That means it's an x equals y squared equation, a negative y squared equation at that, because it's going to the left instead of to the right. Now, the focus, although it doesn't matter, the focus would be right here, right? What does matter is basically the p-value. The p-value is the distance between vertex and focus, or vertex and directrix, but technically this one, because it's supposed to be like negative. So the p-value is -2. That's what we need to establish. P is -2. And that's kind of what establishes what A is. So if A is 1 over 4P, A is -1/8. Now, they give you the vertex at 0, 0, so you have A, you get H and K. H is 0, K is 0 because it's at the origin, and you know it's an x equals -y squared equation. So the final equation is going to be x equals -1/8 y squared. That's it. Now, I was kind of hoping, and it doesn't look like we'll get one here, so, you know, I wanted to show you the standard vertex the vertex form for this when it's an x equals thing. It would have looked like this. H and K also flip. That means the opposite of K here and the same sign for H. So you would have that same effect as you would for the y equals equations. We didn't seem to do that here, but just keep that in mind if you ever have to do one of those. Last question of this portion, number 32. The focus is now at 2, 2, and the vertex is at 2, 6. So let's see which way that's facing. Maybe I can just do a rough sketch graph this time. I probably used to do that. So focus is at 2, 2. Vertex is at 2, 6. So as far as this kind of graph goes, 2, 2 is focus, 2, 6 is vertex. This graph has to go into the focus like that, opens up into it. So it's a y equals x squared equation, a -1 at that. How far away is 2, 2 from 2, 6? 4 away. P is -4 in that case. So it's a y equals x squared equation, or negative x squared equation. All right, that's not the answer. It's just the kind of equation it is. If p is negative 4, a is 1 over 4p, so negative 1/16. And the vertex is at 2, 6. So as far as that, that's your hk. As far as that goes, that's your hk. So your equation, that's a lot of outlining, is going to be y equals, I'm going to use all this room, y equals a times x minus h quantity squared plus k. I was about to write k. I think I was about to write h and k literally when I was saying those out loud. So h and k, and that's the final answer. And it is a negative x squared. P took care of that, but if you forget to mark p as positive or negative instead of positive, make sure you know which direction it goes to remind yourself of what it is. And that should be the answer to that one. Okay, the last section and the last 3 problems we're going to do is focused around here, comparing linear, exponential, and quadratic functions. Now, a quadratic function will have the u shape. Exponential is a curve without the actual u itself in a constant ratio. Linear would be a straight line, of course. Tell whether the data represents linear, exponential, quadratic. So as they plotted these points, they say quadratic. As they plot these points, they say exponential. Part C, you're going to see a constant rate of change as x changes with consecutive increments of 1. So constant rate of change would be what a linear function does. And as these ones, as x changes incrementally, you can see variance this time in the first differences. We do plus 4, then plus 1, then minus 2, then minus 5. But you'll see that those differences has a constant difference of negative 3. Quadratic equations do that. So a quadratic equation does that. What does an exponential function do? It'll have a common ratio. You might be multiplying or dividing by the same number over and over. We like to call it multiplication of the same number over and over. That's what an exponential will do. And that might be what the first question is here. So let's start with question number 33. Tell whether the table of values represents a linear, exponential, or quadratic function, then write the function. So with the first one, this x and y, we have a copy-paste job. And as x changes consecutively by 1s each time here, sorry, that's a little messy, but as we're adding 1 each time there, what's happening on y? Incredible shrinkage to the point that if you notice what's truly, let's kind of start from here. 8 divided by 4 is 2, so you can say times 1/4, and that's what's happening here. 32 divided by 4 is 8. This is a times 1/4 pattern over and over, and you really do want to say times 1/4 or 0.25 when it comes to this being, first of all, an exponential function. They don't ask us to tell you why, but I'm showing you it there. It's an exponential. As far as the function goes, a couple things in mind. Number 1, y-intercept. Y-intercept is right here, the value of y when x equals 0. Our form for exponential functions is y equals ab to the x, and a represents the y-intercept value. So y equals 128, that's your a, and your b value is this 1/4, or 0.25. You can write either or. Here's one version, 1/4 to the x, or 0.25 to the x power, one or the other. Especially when they talk in word problems, you want to use decimals because you could say, oh, it's a 75% decrease each time, and that's a common thing to mention. So there's that one on number 33. They didn't show them in the example, so it's good that we got one for ourselves to do. Number 34, write a recursive rule for the function represented by the table of values. Normally they won't reference a kind of question like this. Well, that's not necessarily true, but unless it's a quadratic. So I think that's looking like a quadratic. It's definitely not linear, and we just came off an exponential, which would be a little rougher around the edges to play with on that. So I'm guessing this is a quadratic, and for us to really hone in on that guess, let's see that there's a constant second difference, and that's relevant to what we do. So there's a first difference of values here that you're adding a different amount each time, but plus 1, plus 5, plus 9, plus 13, is showing that the second difference between these, that the difference has a common difference. That's the way I tend to say it. That you're adding 4 more than you did from before, from the value before. That's not the answer. They say write a recursive rule. Now, a general sense of a recursive rule, especially for something with common difference practices, is to find the value of the next term. You take the value of the term before it and add your common difference. The problem is there's no common first difference, but a common second difference. So D is all about finding the common second difference. What we do is we come up with a rule for the first difference values, almost like a sequence, 1, 5, 9, 13. The rule for this one right here, let's explore that as D, D here. D equals, let's actually use blue. D equals, start with the first term, and you add your common difference of those numbers, n minus 1 times. This is how we want to write that D value out, but simplified. So we want to write it as 1 plus 4n minus 4, or 1 minus 4 is negative 3, so 4n minus 3. So when we write this thing out, we actually want to write our equation as f of n equals f of n minus 1 plus 4n minus 3. And this is the answer. The classic version of a recursive rule shouldn't rely on, see, n is like your x. N is like your x here. It's when n is 0, when n is 1, when n is 2, when n is 3. And I actually have one more thing to mention, by the way. F of 0 is 5. You start from 5, and then you find your first term by taking your 0th term and doing this stuff with it. And you plug in 1 for n. And then the second term you plug in 2 for n, and plug in 3 for n, and that's a part of it. Because your difference is increasing by this amount where 4 is applied, and that kind of helps you out with it. So it might be a weird case where you're saying, I don't know what I'm doing with that. You can go ahead and check out more problems like that in section 3.7 with my video if you want to. And the very last question on this is number 35, where it looks like a word problem. The balance y in dollars of your savings account after t years, this is a true comparison of different functions here, is represented by this equation, y equals 200 times 1.1 to the t power. The beginning balance of your friend's account is $250, and the balance increases by $20 each year. Well, that's a different kind of equation. That's a y equals, this, I'll just make this a system, if you will. A y equals increases by 20 each year. That's 20t plus starting with 250. Compare the account balances by calculating and interpreting the average rates of change from t equals 2 to t equals 7. That's from year 2 to year 7. To interpret some of this for you to start, I think we just understood the bottom one. That's how I wrote the equation. It's clearly a linear equation where you start from this amount and increase this much each year constantly. This equation says you actually start from $200 and you increase by, if you remember 1.1, that's a 10% increase. That's 1 plus 0.10, which is a 10% increase. So it's increasing by 10% every year. But what they want you to do is find the average rates of change between those, the slopes between those ones. I'm going to call this y sub a and y sub b to kind of get it a little better made sense. So the slope of set A, actually let's start with this. The slope of set B. The slope of set B is 20. You increase by $20 each year. That's your average rate of change. Every year it's increasing $20. So there's that one. That's not going to change. I don't have to do a whole slope thing to figure that out. It's given. That's your slope. This one, we have to find the average rate of change from here. That means that from year 2 to year 7, what is that slope? What was that rate of change? How many dollars did you increase on average? Even if it's increasing exponentially every year, we're just finding the line version of it. Not the whole equation, just the slope. So we want to do y2 minus y1. So I want to do 200 times 1.1 to the 7th power minus 200 times 1.1 to the 2nd power over x2 minus x1. The distance between 7 and 2 is 5. 5 years apart, let's divide by 5 for the amount of money we made over that time. This is where I get to use my calculator. I do not have it up. I did not have it prepped. Give me 1 second. I don't need to show you it. I'm just going to type in those numbers. I'm not going to round anything until the very end. So let me just 200 times 1.1 to the 7th power. It'll be some decimal thing. It's around 389. I'll just work this out. Minus 200 times 1.1 squared. By the way, I'm doing the subtraction right now. So the top is going to be 147. It's about 147.74342. That might even be exact, divided by 5. So I divide that number by 5, and I'm getting 29.548. So I'm going to round that to about $29.55. So it says compare the two. This is remember, this is per year. This is per year. That's the slope. That's the rate of change. So on average, this is happening. Was this happening? This happened every year. This happened over the course of those 5 years specifically. What happened from year 0 to year 1? Not that much in comparison. Actually, it probably would have been $20 of increase. but not that much in comparison. This is growing more over time, and that average, listen, from year 6 to 7 was probably significantly more than this. This is just the average over that time, so it's really taken off. So whatever the balance is doing in the savings account is much better than what your friends is doing. I'll just say that as an overall. This one's ruling for savings account interest. And guys, that ought to do it for this one. This is Mr. Robinson. Thanks so much for watching. I apologize for the cooker problem thing. I think I probably cracked the code on what you're supposed to do. But I hope that this all worked itself out because it was hour 45 of goodness. Check out the description section down below if you want to find some more things regarding this or things in my playlist. But y'all, take care. I will see you in the next one.